So my name is Mia Burke. I work with Hanford Challenge as program manager. And Hanford Challenge, if you're not aware, is a nonprofit that's based in Seattle. And we advocate for a safe and effective cleanup of the Hanford nuclear site. And one of the most important things about our organization is the support of workers on the front lines of cleanup and our support of insiders and whistleblowers as well. This is the 29th webinar of our Nuclear Waste Scholar Series. If you're new to the series, we started it to inspire action and involvement with Hanford Cleanup by inviting speakers to share groundbreaking scholarship, art, research, and experience working with nuclear waste. And today we are inviting back a previous speaker on this series. It is my pleasure to introduce Dr. Arjun Makhijani. Arjun is the president of the Institute for Energy and Environmental Research, and he holds a PhD in engineering from the University of California at Berkeley. He has produced many studies and articles on nuclear fuel cycle-related issues, including weapons production, testing, and nuclear waste over the past 20 years. He is the principal author of the first study ever done, completed in 1971, on energy conservation potential in the US economy. Arjun has authored many books, including Carbon-Free and Nuclear-Free, a roadmap for US energy policy, which is the first analysis of a transition to a US economy based completely on renewable energy without any use of fossil fuels or nuclear power. He is the principal editor of Nuclear Wastelands and the principal author of Mending the Ozone Hole. His most recent book is titled Exploring Tritium Dangers. Just as a heads up, if you can't stick around for the whole presentation, feel free to leave. We will be recording the presentation and we'll share a link of the recording with everyone that registered. Thank you so much for joining us today, Arjun. I'll pass it to you to talk about your work.
I should have sent you an updated Vita because I've been doing work on nuclear issues for 45 years and on energy issues for 55 years. Carbon-free, nuclear-free was the first, but it's obsolete. And I'll put in a link to a more current, because it was written when solar energy was $10 a watt. And today it's $1 a watt. So different landscape, better landscape. So I'll put up a more recent transition to renewable energy. I'm going to mention it in my talk. So let me just launch into it. So I'm going to focus broadly on the front part of what's called a nuclear fuel cycle, which is common between nuclear power and weapons. But then I'm going to focus on the power side of the waste problem. I'll go over very quickly most of the waste issues just to give you some context, and then focus on the one thing, spent fuel, that contains almost all the radioactivity. Okay, so this is some basics. So uranium-235 is the only natural fissile material that sustains a chain reaction. It's only 0.7% of natural uranium. Any other fissile materials do occur in nature, but they are very trace quantities and not usable. Thorium, which you hear as a fuel, thorium-230, is not fissile. It needs to be converted to uranium-233. So uranium-235 is the only naturally occurring fissile material. Uranium is still dangerous. It's not very radioactive, 0.7 microcuries per gram. It has some decay products. But as an example, strontium-90, which is a fission product, is 140 curies per gram, more than 100 million times more radioactive than unrefined uranium together with its solid decay products, thorium and radium. By itself, it's 200 times, more than 200 times more radioactive than natural uranium. And that's true. So most of the so we're increasing the amount of radioactivity when we fission uranium greatly. So two takeaways from this sort of introductory basics about what we're doing is by stirring up uranium from the ground, mining and processing it, we're letting loose the radioactivity and the toxic materials in uranium ore. which is for the most part otherwise safely in the ground. We do have uranium in the environment. We do have uranium, uh, as part of what we naturally are exposed to, but very tiny amounts. Fissioning uranium vastly increases the amount of radioactivity. Okay, so I just wanted you to have that perspective of what we're doing. So this is fission. You know about it. So mining, that's ore. There's a lot of mining waste, ore that's not subgrade or not usable. Milling to get the uranium out, you get U3 or uranium oxide called yellow cake because it looks yellow. Yellow powder, conversion, uranium hexafluoride, enrichment. The enrichment is to increase the uranium-235 part of it for the kind of reactors that are there in the United States. The Canadians don't do that for their reactors. But when you enrich it in uranium-235, that's the fuel, about 4% typically, then you get a stream where the U-235 is low, 0.2% instead of 0.7%. So for a kilogram of fuel, you get 1 kilogram this way, you get 6.4 kilograms this way. So for 1 kilogram of fuel, you actually need 7.4 kilograms of input uranium. So that's just some numbers for you. This is a uranium mine, surface mining. This is a uranium mill. So, uranium ore might be in the United States, it was 9.4%, 0.5%, 0.6%. So 99.5% of the stuff is waste. It winds up in mill tailings ponds, contains radioactive materials and toxic materials. We have more than 200 million tons of this stuff. This is uranium enrichment. These are centrifuges. There's a plant like this in New Mexico. Depleted uranium cylinders, as you can see, not in very good shape. There's a fuel assembly. The pellets are, like the eraser on the back of your pencil, that size. This is about 12, 14 feet, the fuel rod bundle of a pressurized water reactor. All right, this is what a reactor is. I just want to tell you, a nuclear reactor is just a boiler. This is just like a coal-fired power plant, except what creates the heat for boiling the water is uranium instead of nuclear fuel instead of coal. In coal, the fire is on the outside. In uranium, the fire is on the inside of the reactor. And the other difference is you can't shut off the fire when you shut off the reactor because you have all these fission products that are extremely radioactive. And typically the meltdowns that have occurred after the reactors are shut. And you wonder why? Well, the reason is that about 7% of the heat is still being generated from the residual fission products. This is spent fuel storage. It has to be stored deep underwater, 15 feet, if I'm remembering, 20 feet, greater than 20 feet, it says, to shield the radiation so the workers can stand around you and manipulate it and so on. Dry cask storage, you have to store it underwater for a few years, but you can then put it in dry cask storage. These are abandoned uranium mines in Navajo country, more than 500 of them. There are lots of them that have high levels of radiation, more than 10 times background. This is a serious, serious problem. These are mill tailings areas. This is a leaking mill tailings pond. I just wanted to give you a little bit of a picture about radiation risk. With age, children much more susceptible, females more susceptible than males, and radionuclides cross the placenta. HT is tritium, produced routinely in nuclear reactors and routinely in nuclear weapons tests and explosions, crosses the placenta. In the fetus, concentration is higher than in the mother. And it can be in the mother before pregnancy, it'll still wind up in the fetus. It's still in the body at the time of pregnancy. OBT is organically bound tritium. So of course it's water. H2O is just water. It gets into leaves, photosynthesis, and then it gets into food and so on. Organic carbon, there's carbon-14, So radioactive carbon-14 is both tritium and carbon-14 are present in nature naturally in tiny quantities, greatly increased by human activity. Cesium-135, 137, these are fission products. They're about the same concentration in the mom as in the fetus. Uranium and plutonium also cross the placenta. The ratios are shown. So my talk is not about this. We can talk about health. But I just wanted to give you a little bit of the landscape of what we're dealing with. So this is where the spent fuel is stored. Mainly, these are the reactor sites. These are the operating reactor sites. We have 94 operating nuclear power reactors in the United States at present. There are about 20 of them that have been closed over the decades, especially since the 1990s. Okay, here's where spent fuel is stored. Lots in Illinois, lots in Pennsylvania. A lot of the nuclear power plants are in the southeast Atlantic and upper Midwest. 2 reactors operating in California, 3 in Arizona. I don't remember how many there are in Texas. Maybe 4. I don't remember. Okay, so what happens? So this is, talking about spent fuel, we have to know what it is. So about 4%, we increased uranium to 35 to 4%. These are percentages to 4%. There's a trace uranium, which is uranium-234, which is a decay product of uranium-238, actually. This is 0.04 is uranium-234 because it is in enriched uranium. Natural uranium is 0.005. This is 4% enriched uranium composition. So everything is 0 except for U-234, which is the top line, U-235, U-238. So what happens when you operate it? You decrease you're fissioning uranium-235. You go from 4% to 0.68%, about the same as natural uranium. You create a new isotope, which is not present in nature, which is a headache for nuclear power operation if you want to reuse the uranium. You decrease the amount of uranium-238. Now, it's not fissile, so what is happening? Some of this uranium-238 becomes plutonium. And so as you boil water, you're creating fission products. There's 4.6% fission products, but you're also creating plutonium. You see, we've only used up 3.3% of the uranium-235, but fission products are 4.6%. So where did the extra fission come from of uranium-238 is not fissioning in the kind of reactors we have. It can fission with fast neutrons, but we don't have fast neutrons in these reactors. They are moderated reactors. What is happening is neutrons are absorbed by uranium-238. Plutonium is made, plutonium-239 first, and then other higher isotopes, 240, 241, 242. And in spent fuel, after about 3 years of operation, a spent fuel bundle will have about 1% plutonium isotopes. About 60% of this is, a little less than 60% of this is plutonium-239. And about 15% is plutonium-241, both fissile. So this, if you separate the plutonium, this is bomb-usable material. It's a big part of my story. That's why I'm dwelling so much on it. There are also non-plutonium transuranics, neptunium-237, americium-241. They are nuisance radioactive materials, very important for waste disposal issues because they persist. Neptunium-237 has a half-life of more than 2 million years, if I'm remembering correctly. Okay, so let me give you an overview of what we're talking about when we make spent fuel. We have 90,000 metric tons of spent fuel stored in the United States from operation of nuclear power reactors so far, a little bit more than 90,000. The plutonium in it can be used to make bombs if it is separated from the spent fuel, about 100,000 Nagasaki bombs worth. Of course, worldwide, there's a lot more than that. Largest nuclear power plant in Europe is now in a war zone. It's occupied by Russia. Uh, a lot of people have been, including the IAEA, have been trying to, calm things down over there and make sure there's more cesium-137 in that spent fuel at Zaporizhia than was released in all atmospheric nuclear weapons testing from all nuclear weapon states. Okay. So what you're doing when we use nuclear, we should know what we're doing, right? We're making plutonium, and we're creating long-term bomb risks to reduce CO2 emissions. That's a very important point I want. That's inherent in the process. And you can say we can separate the plutonium and use it as a fuel. I'll come to that. Currently, so people have separated plutonium from civilian spent fuel. The French have done it. The United States did it for a little while. There was a plant in West Valley, New York. There's some surplus. That plutonium was never used, to my knowledge, or almost none of it was used for fuel. But worldwide, starting with Britain, second France, Russia, Japan, India, they have separated bomb-usable plutonium from the civilian sector of more than 300 tons, which is more than the double of the plutonium weapons stock in all nuclear weapon states. So this is a startling thing that very few people know, but everyone should know that the commercial sector, it's stored in, you have your stainless steel tin for sugar or something. It's stored in tins like that. It can't be stored in bulk because of the danger of accidental criticalities or chain reactions. So it has to be stored in small amounts. And so it is stored like that in the countries that I've mentioned. This is what happened. These are fission product curves for different fissile materials. Blue is plutonium. Green is uranium-233 that is made out of thorium-232. Red is uranium-235. And black is, I think, the mixture of materials that you find in light water reactors, which is a mixture of, so some of the energy is created by the fissioning of plutonium as the reactor operates, because plutonium is made in the reactor and it's fissile and it fissions. And you can see the fission products are concentrated in two parts of the periodic table between about 80 and 110 mass number, and then about 130 odd to 155, something like that. So this is a very interesting thing. Most of these things are highly radioactive. Some have very short half-lives. The radioactivity per gram is inversely proportional to the half-life. So the shorter the half-life, the more radioactive. But, tritium has a half-life of 12.3 years, but it's extremely radioactive. So you get less radioactive materials only when you get to very long half-lives of, hundreds of thousands or millions of years or billions of years. Okay, so these fission products are very dangerous. Iodine-131, 8-day half-life. And it's decayed completely, almost completely in a few months. But it's very important in the case of accidents. It's been very important in the case of atmospheric nuclear test explosions, and estimated to be responsible for tens of thousands and up to hundreds of thousands of cancers from Nevada, between 11,000 and 212,000 thyroid cancers from Nevada test site, atmospheric testing alone. That was the estimate of the National Cancer Institute made in 1997. There are short-lived noble gases. Noble gases are not reactive. So you breathe them in and breathe them out. They're not very dangerous in that form, but they decay sometimes into radioactive material. Cesium-135 is an example. Half-life of cesium-135 is in excess of 2 million years. So, inversely proportional to the half-life, but cesium-235 still packs a punch, much bigger than uranium. very long-lived radionuclides. Carbon-14 is created as an activation product. Half-life 5,730 years. Technetium 212,000 years. Iodine 129, 16 million years. Neptunium 237 already mentioned. These are important because long half-life materials, they're locked up in spent fuel mainly, but they're, the spent fuel rod, we're talking about hundreds of thousands, millions of years. It's generally expected that this will deteriorate and leak into the environment from a repository. So you have to consider what happens. The main impacts from repositories are generally via groundwater. Tritium is the most ubiquitous pollutant in weapons and power. Half-life 12.3 years. Crosses the placenta, just like water. So it pervades every single cell. I've written a whole book about this because it's a very neglected radionuclide, unfortunately, because for grown-ups, it doesn't matter except those who can become pregnant and then during pregnancy. And my sort of, I've been a broken record on the problems of radioactivity exposure, especially for radionuclides that cross the placenta. And I've used tritium as sort of the example because, we say water is life. And so tritium combined with oxygen gives you radioactive water. So it makes the stuff of life a radioactive poison, basically, that pervades every cell and crosses the placenta. So all reactors produce this and rain radioactive rain on their neighbors and dump it into water bodies in their neighborhoods, whether it's the oceans, lakes, or rivers. All right, so strontium-90 mimics calcium, cesium-137, major fission product, also both of them mimics potassium. They have relatively long half-lives. So the story that many of you may not have heard is the story of spent fuel, and that's why I chose to focus on civilian nuclear power. I've spoken on Hanford before to Hanford Challenge folks. So cesium-137 is a powerful gamma emitter. And so, if you remove a spent fuel bundle from a reactor after 3 years, it would be lethal, I think, in under 1 second if you approached it very close. And so it's extremely radioactive. Most of that radioactivity is due to short-lived fission products, but they decay away. So after a few years, after 10, 15, 20 years, most of the external radiation, that is the thing that makes it dangerous for you to approach spent fuel, is from this one single radionuclide, cesium-137. So it has a half-life of 30.1 years. So that means there's still half of it after 30.1 years. After 10 half-lives, there's about 0.1% of it left. So 99.9% is gone. And so, you may still have a fair amount left, but the external radiation will be quite low. And so that is today, there are two things that, if you don't separate the plutonium, there are three things that are moderating greatly, keeping that plutonium secure and away from a weapons production cycle. One is the power plants are operating, there are guns and guards, there's security. Second is it's extremely radioactive and difficult to carry away. You have to remote handle it. And the third is there's no real incentive to remove the plutonium for states that already have lots because they already have weapons usable plutonium. So today, but what happens when nuclear power plants shut? Like you could extend the life for 60 years, 80 years, et cetera, et cetera, et cetera. But eventually they're going to be shut. They're going to be shut in a time that's much smaller than the half-life of plutonium, which is 24,110 years for plutonium-239. That's longer than, any written records. We've had a new pope elected. The Catholic Church has been around for less than 2,000 years. So And Augustinian. So Augustine was one of the philosophical founders of the Catholic Church. He was around 4th century BC, AD. So say 1700 years in kind of more or less its present form, 1800 years. So we're talking about a half-life of plutonium that's more than 10 times the longest sort of stable, and not without its scandals, if I might say so. So stable doesn't mean 100% integrity. So we have a situation where the economic interest will decline, the plants will be shut, the whether there will be money to protect this and for how long is an open question. I'm going to talk about that. I think it's in the next slide. But the physical issue is that after 200-300 years, the whole problem of theft of spent fuel or other diversion becomes completely transformed technically from what it is today, because now you no longer need remote handling to carry it away. You need a hefty crane and you need a hefty truck, but you do not need remote handling. And the same for the chemical processing that is required for extracting the plutonium. Today, you need remote handling, and you're going to have highly radioactive fission products. The most problematic being strontium-90 and cesium-137. And the most problematic ones will be gone in 300 years. Strontium-90 half-life a little over 28 years. And so, if you are a malevolent group, a state that does not have plutonium and wants to make nuclear weapons, now it becomes much, much less difficult to get the plutonium. Does extracting the plutonium and using it in reactors solve the problem? So this is why breeder reactors, sodium-cooled breeder reactors, had been thought of. Uranium-238 will turn into plutonium. We'll put it in the blanket. We'll have a magical energy source forever. Sodium-cooled reactors did not work out after $100 billion with a B worldwide expended since 1951 to today's type of dollars. So inflation adjusted. Even if the reactors, some of them have worked sort of well, some of them have not worked well, but it has not been commercialized. So France has separated plutonium. They kind of went on with it even after their breeder reactor program was failing, but they used plutonium in light water reactors. Light water reactors has the problem that, they use 1/3 plutonium fuel, what's called MOX fuel, but you can use it repeatedly. This Sankey diagram, you can study the numbers in it later, but less than 1% of the underlying uranium resource is eventually used up. And because it's so difficult to reuse the plutonium that's created, once you've run that plutonium once more through a reactor, we have lots and lots of plutonium piling up in the commercial sector, more than 300 tons, as I've told you. By the way, International Panel on Fissile Materials, which is based in Princeton University, has lots of reports on this, and you can go and check out all numbers. So these are some data, global military stockpile, civilian stockpile. And so I've already talked about this. I won't dwell on it. So I can tell you this story. It's a very bizarre story, and I've been personally involved in it, in the lawsuit as an expert. And in the 1970s, when these regulations were first being created, you don't need to read this. I'll tell you the story. The Nuclear Regulatory Commission essentially said that we're going to have reprocessing. There'll be liquid waste. They'll be vitrified. We'll find a repository and be disposed of in a repository. 1982, there was a Nuclear Waste Policy Act, and there was a provision in that for 2 repositories. Reprocessing had been stopped by this time. Carter had stopped it. President Reagan tried to persuade private companies to open a nearly completed reprocessing plant in South Carolina. No, there were no takers. And so basically reprocessing ended in the United States. Some still talk about it, but it's, I think it's whistling past the graveyard of reprocessing in the United States. Uh, so we've got all this spent fuel piling up. And every now and then, the NRC would publish what was called a waste confidence rule. And they would reaffirm their confidence that there would be a geologic repository for spent fuel disposal, because that became the policy in 1982. And, in 1982, there was a timetable for creating a repository. We can talk about it in Q&A as to what happened to that, but there was supposed to open a repository by January 31, 1998, and it didn't happen. And as it turned out, the chosen site that became a political process. Yucca Mountain, in my opinion, is a pretty bad site. I do support, reluctantly, a geologic repository as the least bad solution. I'll mention that a little down the road here. But for this story, the NRC published this we're confident there'll be a repository. There was good reason for confidence in the 1980s, less as the 1990s went along. And then as the 2000s wore on, it became clear that Yucca Mountain was a bad site. There was a lot of opposition to it. The senators from there became more powerful than the time in the 1980s when it was named as the sole site, the very same senator, Senator Reed. And then President Obama canceled it. So now, the whole program is pretty much dead. And the NRC is saying we're confident there's going to be a repository, and there's no basis for this confidence. So there was a lawsuit, and the NRC was asked to, not say there's going to be a repository in Finland, so we're confident there'll be one in the United States, to talk about the United States repository. And so, long story short, what the NRC did is that they said we're confident that it'll be a repository, sometime, not in the decades to come, but it doesn't matter if there won't be a repository. So that was the new part. This is in 2010 or something. It's called the Waste Confidence Rule. And they said that if there's no repository, we're still confident everything will be fine. The spent fuel will be securely stored. The government will be there. So even after the plants are shut, the government will be there to appropriate money every year for the guns and guards. These are not the words in the waste confidence rule, right? You have to understand what the waste confidence rule said, and you can go and read it. But this is the clear implication of what they said. And that every 100 years, if necessary, these containers might rust and rot, and the government will appropriate more money to change out the containers, and there'll be the cranes and the equipment to do it. And the NRC will be around to supervise, to make sure that it's properly done. How long? 100 years, 1,000 years, 10,000 years, 24,000 years, forever. So they said it was beyond plausible. I forget what the legal term was. It was unreasonable, to imagine that the US government would no longer be there, and that the NRC would no longer be there. And unreasonable also to say that Congress would not appropriate money to look after this stuff. Ignoring the fact that this country had a war of independence less than about 250 years ago, starting now this year, 250 years. It had a civil war. There'd be 2 world wars. The government has been shut down a number of times when Congress has refused to appropriate money for brief periods of time, even to keep the government operating. So these are, of course, government operation functions. And so we're talking about this over a period of about 250 years, which is 1% of the half-life of plutonium, and 0.1% of the amount of time you need to look after this stuff, which is longer than the history of humanity, the longer than history of any institutions, the longer. Yeah. So They said they're confident that even though there is, even in the NRC's other rules and National Academy, so this isn't just Arjun Makhijani who's saying, that management of these kinds of long-lived materials should assume that institutional control, that is governmental control, and so on, will be lost in 500 years. So that's even longer, double the, 500 years above the Columbian era, basically. There's been a lot of turbulence in the last 500 years. But still, and now, we see in front of us the war in Ukraine going on and the drama around the Zaporizhia plant for more than 3 years. All right, so so we've got a problem, right? We're in the middle, we've created all this stuff. There's nothing to do with it. It's very dangerous. We're the NRC, in my opinion, and this is an opinion, and I do think that the French regulation is more, for instance, more strict than the US regulation. And I can give you examples if you want during discussion. The NRC has allowed re-racking and dense storage of spent fuel in spent fuel pools. Ostensibly, it reduces the cost of of getting it out and storing it in dry storage. After 9/11, many of us advocated that there should be low density, open frame spent fuel storage so that if there was a loss of coolant, the risk of fires would be low and a high dispersal of radioactivity. During Fukushima, there was actually, fear that the spent fuel pool in reactor number 4, if I'm remembering correctly, would lose its cooling water and cause a meltdown and a fire in the spent fuel pool and a massive release of radioactivity. Remember, the long-lived radioactivity is accumulated in spent fuels. So the long-lived radioactivity in spent fuels is much more than the long-lived radioactivity inside the reactor, because the reactor only contains 3 years of fuel, but spent fuel pools now contain 20, 30 years of spent fuel. And they did not require that. We advocated for hardened dry storage. So these were my recommendations and they're taken from my presentation to the Blue Ribbon Commission under President Obama in 2010. So this is what I advocated: store spent fuel in hardened storage. So any malevolent attacks would, have a very, very low probability of offsite massive fallout. And some places may be unsafe for storage. There's no safe place as such in terms of zero risk, but some places have higher risk than others. We have sea level rise, all of that. So there may be some necessity to move this stuff. And we can argue where, and everybody would want it out of their neighborhood, but I generally don't go there. If you move it to a centralized storage, it just creates one more place of storage, and I think needlessly increases the risks. So that's sort of my take on what the interim situation. For the long term, deep geologic disposal is the least worst approach. So in the American University neighborhood in Washington, D.C., which is a pretty fancy neighborhood, the US military had a chemical weapons project in their area during World War I. And then it was closed, and there were a lot of highly toxic chemical waste that had been dumped there, and everybody forgot about it. So in a 60-year period, this had been forgotten. Now the EPA has been created. There are lots of fancy houses in the neighborhood, and not to speak of a university. And then this was discovered in the 80s. Everybody forgot about it. We're not talking hundreds of years or thousands or tens of thousands. We're talking less than a century. And then when it was rediscovered in the 1980s, nobody wanted to deal with it because of a fancy neighborhood, but children are playing here. So I don't want to go into the evolution of how, eventually they decided to deal with it. I'm not a scholar in it. They did, but just to illustrate that loss of institutional memory is a thing, that it's a demonstrated thing. In the short term, relative to the time scale we're talking about. So if you leave this stuff around and you've lost the external barrier, now you have a weapons problem that is a proliferation issue to which I don't know that anybody has any answer. Certainly, I do not. I do not know of any institutions that could look after this stuff for that long and have the power of control over the plutonium and not be somewhat have a tendency to corruption. I illustrate part of the dilemma of spent fuel. I made a presentation to a National Academies Committee about some of this stuff about 20 years ago. And I posed the following question to them. So we say there'll be a report, how difficult this problem is. Everybody says, so people who've thought about this problem say deep geologic disposal, put it in a remote area, put it very deep, have barriers, it'll be very hard to recover. And all of that is true. That would be much more secure than leaving it on site forever and saying the government is going to be there, the way I've told you. So I agree with that. But then they say we should leave markers, that people will be able to understand 10,000 years from now. And so the markers will obviously say, there's dangerous radioactive waste buried here, don't go there. So the question I posed, people who are, luminaries in this field, if I might say so, or scholars in this field, is that we assume that if everything works out and the markers do their job, people will be able to read them and understand them. And we're assuming that everyone who reads them and understands them is going to be good. But there's no basis in history to make that assumption. So now we've put spent fuel in a remote area deep down with a marker saying, basically, there's plutonium down there. Someone is going to say, nobody's looking, maybe I want to go down there and get it. The history would certainly lean in that direction. I'm not saying it'll happen, but certainly something we should think about. So I said, maybe it might be better to put it under a big city and without a marker, just as a thought experiment, not as a recommendation, mind you. So that and then no marker, so that we would forget about it, lose the institutional memory. And in the future, the archaeological interest in the upper layers, because you're talking about a city, right? Pompeii, for example, would be so great that nobody will go deeper. So the risk of recovery of the plutonium in the future would be much reduced in this thought experiment. So that, we should rethink how complicated this question is and how complicated the marker issue alone is. There was dead silence when I asked this question. There were about 20 people in the room, if I'm remembering. Anyway, many. And I never did get an answer to this question from anyone over the last many years. I don't think there is a good answer to this question. So now nuclear power is a low carbon energy source. Tens of grams, everything has some carbon associated with it, solar, wind, nuclear. So long as you have carbon in the energy economy, everything is going to have some carbon associated with it. But you can imagine a purely solar, purely nuclear, purely, as a thought experiment, I'm very fond of Einstein and I'm very fond of thought experiments. Purely nuclear, purely solar, purely wind energy system that would have zero carbon emissions. So there is that. But I spent 4 years coming to this conclusion for Maryland with hour-by-hour modeling. The report is Prosperous Renewable Maryland, 2016. All electric heating, all electric transportation. So I concluded that we could do it all with basically wind, solar, and existing hydro. I don't even think we need existing hydro. We can do it without existing hydro if need be, or places where there's little or no hydro. There's very little hydro in Maryland anyway, 2%. And that it could be done reliably and cheaper or less costly than business as usual. These are the kind of distribution of how the loads were covered. Electrons must go on. You got to have a reliable, you can't do it, people who say, well, you know, the wind doesn't blow all the time and the sun doesn't shine at night. I know that, you don't have to have a PhD to know the sun doesn't shine at night. You can just, open your eyes. And, but you do need to make some effort to come to this kind of conclusion. It's not a slam dunk, it's complicated, it's difficult, but absolutely it can be done. And today, this was 8, 9 years ago. Today, it could be done much better because technology is much better today. So here are my conclusions, and I'll stop here. There's no good solution to the problem of spent fuel. There's no good solution to all the hundreds of millions of tons of mining and milling waste. The United States is importing more than 80% of the uranium for nuclear power plants. So we're exporting environmental injustice, the mill tailings, the mine waste, and so on and so on. Imports are Kazakhstan, Canada. I have the list somewhere. We're making plutonium to boil water. If we have alternatives, to me, it doesn't make sense. We have alternatives that are cheaper in my calculation, and those alternatives obviously have to include the fact that electricity has to be reliable, and it can't be reliable by just hooking up wind and solar plants. But the wind and solar can be the primary energy supply, and you can arrange the system so it works. And in my opinion, cheaper than alternatives. The security problem with nuclear power is at least as grave. In my view, it is the most grave single problem with nuclear power, for which I do not see any solution. It's already very serious. As I've told you, there's more than 300 metric tons, more than all the nuclear weapons in all nuclear weapon states in the civilian sector that's just sitting around. The end.
Thank you so much, Arjun. You've given us a lot to think about, and additional thought experiments are coming through in the chat and the Q&A. So thank you so much for sharing all of that with us. I learned a ton of things I didn't know about before. And I think we're going to open it up to questions now. If people can put questions in the chat or use the Q&A feature.
Look at them. I'll let you do that, right?
Yeah,
Otherwise, I get
I'll read them.
distracted.
Yeah, I'll read them off to you. So we have one related to the current administration. How are Trump's policies and cutbacks on nuclear safety impacting nuclear power?
I don't know that there have been explicit President Trump policies to reduce regulation in the nuclear power sector. I'd be happy to be corrected. I'm not following nuclear power closely these days. I have written about small modular reactors. I kind of do some of it, but it's not about 20 years ago, I decided I've said everything I want to about nuclear power. It's all out there. It's on our website. People can use it. And, I say things like about SMRs and so on from time to time and do this kind of event. But I don't do a whole lot of work on it. So I'm not keeping track of everything. But to my knowledge, there's been no serious loosening. There's talk, of course, of saying, make it easier to certify reactors, make it easier. But I don't know that anything has been finalized. Somebody on who's participating may know better. But I'm not keeping up with it.
Okay, yeah, thank you. We have some questions around fusion reactors, thorium reactors, concern with tritium being a main breeding material for fusion plants. Can you speak to to that, tritium not being as harmful, boasted as being not as harmful as other radionuclides?
Yeah, so let me address the thorium thing first.
Okay.
So thorium reactors would be the same as fission reactors. That's the kind of reactors we have in principle. You split apart uranium-233 that is made from thorium-232. Now, thorium-232 is abundant in nature, more abundant than uranium, they say. But it's not a fissile material, as I've mentioned. So you have to convert it into uranium-233, for which you need a starter fissile. You need a reactor. So you need uranium-235 or plutonium or something. Apart from an Air Force reactor in the 50s that operated, I think, for a few hours, if I'm remembering correctly, there was a test reactor, 10 megawatts thermal, that was built in Oak Ridge around 1966 and operated off and on with, I think, 200 plus shutdowns over 6 years, and then was shut. And that was supposedly a prototype for a thorium reactor. They never put the thorium cycle into motion there. They used plutonium, they used uranium-235, they used uranium-233, even if I'm remembering. This was Alvin Weinberg's brainchild, and there's a whole fan club around this reactor, molten salt fuel reactors. It doesn't have to be thorium. And so there are pluses and minuses to every reactor. I can go into it, but I don't want to in this particular case. But I'll tell you, this reactor cost about $10 million to build. It was 10 megawatts thermal, or less than 10 million in those days. So today's 60, 70, $80 million in today's dollars. And the decommissioning costs, it's very difficult to handle fluoride fuel as waste because it's unstable, unlike the waste we have, which is uranium oxide, which is very stable. It's a ceramic. So you have to process. The decommissioning cost for this 10 megawatt reactor thermal that never generated any electricity and wasn't designed to, and to handle the uranium-233 that's there, are north of $400 million. And 50 years later, it hasn't been decommissioned yet. Alvin Weinberg, toward the end of his life, to his credit, said, if I had to do it over, I really would pay more attention to the problem of nuclear waste. We didn't do that right. Carol Wilson, manager of the Atomic Energy Commission in the 50s, said the same thing, looking back. But apparently the fans of these reactors have forgotten what the gurus of the reactors said, so I'm here, I guess, to remind. So much for thorium reactors. There's a lot to this story. I did a Science Friday show. It's on our website in 2000 and something about thorium reactors. So you can go to our website and find Science Friday, and it'll come up. You can listen to entertain yourself for an hour. And fusion reactors. So I did my doctorate in fusion, obviously. There are many types of fusion reactions. Tritium, I wrote a book on tritium because it is a very disrespected radionuclide in terms of its risks. And there's a technical reason for that. If I, drink water with tritium in it, it'll pass through my body pretty fast in days. So the cancer risk to me is pretty low. It also would be true for females. Now, when it comes, but that is not the main problem with tritium. There is a cancer risk to all radiation, but cancer risk from other radionuclides, strontium-90, for example, much greater. And, drinking water standard for strontium-90 is 8 picocuries per liter in the US. And for tritium is 20,000 picocuries per liter. And because it doesn't target any organ, it goes all over, so it's more dilute in the body, and strontium-90 goes to the bone. And it passes through the body faster, much, much faster than strontium-90, depending on the chemical form, strontium-90. But it crosses the placenta. That's why I showed that in the beginning. So tritium occurs naturally. It's made in the atmosphere for interaction of the atmosphere with cosmic radiation. but in very trace amounts. The total amount of tritium stock in the atmosphere is a few kilograms. You would need more than that in a single large fusion reactor. So we're talking very large amounts of tritium. Where this tritium would come from is a mystery because you have to make it. Tritium has a half-life. So deuterium is found in seawater. It's not radioactive. It's not a problem. So, but DT reactions, deuterium-tritium reactions, are the most. So you asked me a complicated question about which I know quite a bit. So you have to bear with me. So DT reactions are the least difficult fusion reactions. They are nuclear reactions. They're not chemical reactions. The reason they are so difficult is you need temperatures roughly 10 times the interior of the sun to have enough fusion reactions to give you a net. So you have to heat something up. So of course, 10 times the interior of the sun, and much before that, everything would melt, right? So it cannot be in contact with any container. So these reactions have to occur in a vacuum. So you have a vacuum, so you have DT ions, and then you accelerate them, and they bang into each other with very high speed. That's how they are positive charges, so they repel each other, what you learned in high school physics. And that's why you have to have this very high temperature, so they overcome this repellent force of positive charges and bang into each other and fuse. And then you get a lot of energy. So there's a lot of tritium involved, but tritium is hydrogen. It, gets into the metal surfaces eventually and becomes hydrides. You don't consume all the tritium you inject into it, maybe 10, 15, 20%. Just like the nuclear fuel, you don't consume it all. You stop the reaction because it's not economical to continue it. So then you have to recover it. You try to make more tritium in the blanket, lithium-6, then you have to recover it. If you don't recover essentially all the tritium that you haven't used and make enough in the lithium-6, you're not going to make this work. And you're likely to have significantly more emissions of tritium than what we have. So if you read the serious literature, there's a Bulletin of Atomic Scientists article from a few years ago from somebody. I haven't spent my life working on fusion. I didn't work on fusion after I finished my PhD. I worked on energy issues and more broadly. But there's a very thoughtful article from a few years ago, somebody who worked in fusion all their lives. Deuterium-tritium reactions are the easiest from a physics point of view to achieve, least difficult, I should say. But from a point of view of making it work, and having a closed cycle, it's going to be a total nightmare. And the other thing is that fusion generates 14.6 MeV, mega electron volt neutrons. 14.6 MeV is a very, very extremely energetic neutron. Fission neutrons are 5 MeV, and then they become thermalized, less than 0.1 electron volts in the reactor. That's what moderation means. So you're talking neutrons that are very energetic, that bang into the metal walls and damage the metal walls. So a problem from when I finished my PhD in 1972 was that what are you going to do about the materials damage to the walls from fast neutrons banging against them? The answer was shut the reactor down and change out the walls. So you have to do this now you've got a reactor that costs $10 billion, you've got to shut it down. The walls become radioactive with activation products. So you have some radioactive waste, much less than with current reactors, no fission products. But who's going to buy a reactor in the best of worlds that's so expensive that you have to shut down for months, get rid of the radioactive waste, replace the reactor walls, and then restart? I think if it works perfectly, nobody will buy it. And I don't think it's going to work perfectly. That's an opinion, obviously. Nobody's got a perfect crystal. There are a lot of people maybe smarter than me. I'm sure smarter than me in these kind of terms that are pursuing this, and I'll say mea culpa and confess I'm wrong if I'm wrong. That is the hallmark of Institute for Energy and Environmental Research. You find errata on our website. I'm not perfect all the time. I recently had to confess to a mistake I made, and I did. It was very hard, but I did it. And that, it's good science and honest public work. There are reactions like boron proton reactions that generate only charged particles. They need 10 times the temperature of DT. So now you're talking 100 times the temperature on the inside of the sun. Very, very hard. So I don't oppose, so people say you're anti-nuclear. I said, no, I don't oppose fusion research. I think it has a lot of positive spin-offs. DT, I would not encourage because of so many problems, and the tritium things have not been addressed. Crossing the placenta, malformations. This is a big. There are no protections for pregnant women of the general public to date, although we've known about the problem of severe birth defects since the time of the testing in the 1950s. So I think there's some kinds of fusion research that should be supported more than they are. But in the tens of millions of dollars, hundreds of millions, not billions. I think the 25 billion euro machine being built, ITER, is going to eating up everybody's money. That's, there'll be some interesting technology for measurements to come out of it, diagnostics to come out of it. But in my opinion, nothing else. I probably won't live to be proven wrong on this because they don't even intend to fully start it up for 10, 15 years or something. And I'm already 80, so.
Thank you.
The next question, I'm sorry it takes so long, but you asked two questions, both of which are quite complicated.
No, that was great. Thank you. And we getting thanks from the people that asked the questions. So we have a lot of people asking about your slides. I'm going to include those in an email that'll go out with the recording later.
Yes, I'll send them to you.
Everyone can be sure that we'll share the resources after this. I do have a question. If you're able to speak about reprocessing needed in molten salt fuels, can you speak?
Yeah. So molten salt fuels, I haven't studied all of them, but I can talk about the reactor that was built in Oak Ridge, and there's a lot of literature on it. And it's not necessary that you should reprocess. If you have thorium-based reactors, you're going to have to reprocess because now you're making uranium-233 that you have to extract from the mix of fission products and stuff. So for thorium reactors, reprocessing is necessary. And that was the design of the reactor that was built at Oak Ridge. That was a molten fluoride salt reactor. And the idea is that you have inline processing, so reprocessing. So you have a fissile material, plutonium-239, uranium-235 in the reactor to make the chain reaction going. You have thorium in the molten salt. So some of the thorium-232 is now being converted into uranium-233, and the 230, then you cycle the molten salt through a reprocessing machine, and you separate the uranium-233, and then you have your fissile material for the next reactor. Unfortunately, the rate of conversion of thorium-232 to uranium-233 is pretty slow. So you're going to have to need plutonium-235 for a very long time and quite a few reactors in order to build up your uranium-233 stock. Now, uranium-230, you don't get rid of the the proliferation problem because uranium-233 is bomb usable. They say that because uranium-232, which is highly radioactive, is created along with, but, and I've written about this and others have written about this. If you're desperate for fissile materials to make a bomb, you can arrange to reprocess the thorium, irradiated thorium in this kind of arrangement. So uranium-232 doesn't build up a whole lot. Just for the technical physics reasons of how this particular cycle would operate. And so, and this is apart from all the cost and radioactivity questions. One of the things that people say is that about molten salt reactors, and just to give you a little bit of somewhat amusing, my amusing take on this, is people say, well, you know, reactors we have meltdown risks. Obviously they do, we've had several of them. And molten salt reactors don't have a meltdown risk. Of course, they don't have a meltdown risk because the fuel is already molten. You know, so if your fuel is molten, the volatiles are going to evaporate. So in the present arrangement, there's a meltdown risk in case of accidents. But you have 4 barriers between the radioactivity in the fission products and the environment. There's the ceramic pellet, there's the fuel rod, there's the reactor, water and vessel, and then there are the filters. In molten salt, you only have 1 barrier because the thing is already molten. It's just the filters. And so, and then you've got the molten salt, which is a very hard waste material to handle. A lot of the reactor proposals that are being put forward in the advanced reactor arena are being put forward without serious consideration of what would happen with the waste. Similarly to, you know, the carbon moderated, the TRISO fuel, you know, the reactors with graphite encoded fuel. There's no meltdown, you know, they won't melt down, very high temperature. Agreed. But Windscale with a graphite moderated reactor with carbon dioxide coolant, I think so, no water, no, you know, no steam, no meltdown. But the carbon caught fire. Carbon catches fire. So if you have a helium-cooled graphite-fueled reactor and you lose coolant and air enters into it, what could happen? You've got hot graphite in contact with oxygen. Okay, so you have to, of course, people who advocate certain reactors will want to raise money from venture capital. That's their job, you know. I mean, I think they should be full of public disclosure, but, you know, it's a caveat emptor, buyer beware kind of situation. But for the independent evaluators, for government, for the regulators, the NRC just can't continue to say, you know, we've got confidence that there'll be a repository. What's going to happen to the repository when you put carbon-14 loaded fuel inside the repository and it becomes oxidized? How much carbon-14 are you going to pollute the atmosphere with? It's a question. It was a question even for Yucca Mountain. I was on the EPA committee that addressed that question. And we said, oh, maybe, oops, you know, this is an issue. And there were industry people, there were national lab people, there were the odd guy like me on this committee. So it was, you know, not an environmentalist committee. So, you know, thoughtfulness about what we are doing is very important, especially when you're involved with the kinds of materials that we're dealing with. Pebble bed reactor, yeah, that's another one of them. I call it pebble bed of nails reactor. Nobody laughed? Okay.
I mean, this kind of speaks to the waste confidence rule that you talked about and how
Yes.
it's completely out of touch with reality. This that we don't need a geologic repository. It's like for
No,
future.
they did. No, they don't say that. They don't say we don't need one. They're still confident we're going to have one, but the court asked them to say, what would happen if there's no repository
Yeah.
because you haven't demonstrated a basis for your confidence in the United States? And then they said, we're sure there'll be a repository, but if there's not one, we're confident the government will be there essentially forever. And the NRC will be there forever.
Yeah. Which is
Yeah.
just,
It's very bizarre. Yeah, so if you ask them, are you out of touch with reality? Is Diane Curran on the call? She was the lawyer. We said, basically pointing to the historical facts that you're out of touch with reality, but the NRC said, no, we're in firm touch with reality. It's unreasonable to think otherwise, and the courts agreed with them and let it stand. I don't know if we went back to court. I don't remember the details about where it ended legally.
okay. We have a lot of questions.
Yeah, I'm happy to stay.
We're not gonna get to them all. Just trying to find something. I guess what would criticality look like in irradiated fuel casks or pools at a repository?
Well, to the best of my understanding, there wouldn't be like a nuclear bomb explosion. Because the force of the criticality, the forces generated would cause the material to be dispersed, and the criticality so you may have an oscillating problem. You have you may have damage to the containment. It's not a problem that I've studied in detail, but I don't think it's very difficult to create like a kiloton explosion. You have to bring together a certain amount of mass of material. So if you dispose of spent fuel, you're disposing of material, in those tiny pellets in a vertical configuration, in a geometrical arrangement where a bomb type of supercritical. So a bomb is not just a criticality. A bomb is a supercriticality. You have to achieve, I don't know, 68 something, many what they call generations, a fission with surplus neutrons, another fission, and you have to create that in less than a microsecond. So you're not going to have that, to the best of my understanding, with the current spent fuel disposal program of the United States.
Okay.
Which I think is the best we can do given the problem we've created. But you have to have, I said it should be science-based and then consent-based, and we haven't done that. So while the idea is, I think, should be supported, I don't think the process has been good.
Yeah. I think we'll end there. Thank you so much for
taking. All right.
And thank you everyone for joining us today.
Sorry, I couldn't get to all the questions. Do I get to choose one maybe to answer that I may not have?
Of course. Yeah.
Why is nuclear energy called low CO2? I don't know how much CO2 will be emitting in waste management, but just remember, I mean, the Finns have created a repository. I think I haven't done the calculation, but remember the amount of energy produced in a single reactor is very large. So 1,000 megawatt reactor has about 3,000 megawatts thermal in that one reactor vessel. Give you an idea of how much that is. That's the equivalent of heat generated by 30 million people. Yeah. So the amount of energy that a single reactor generates over 40, 50-year period itself is vast. And then you're talking about 100 reactors. It's an absolutely vast amount of energy. It'd be very, very difficult to spend a fraction of that energy, gathering it up and putting it in a mine. This is not a calculated, studied opinion, but good question. Somebody should do the calculation. It ain't going to be me unless somebody sends me a lot of money. Because it's not a high priority question for me. That's what I mean.
Yeah, yeah. Well, thank you so much, Arjun.
Okay, you're welcome.